Okay, just now we stopped at line defect. Okay. What about planar defect now? Planar defect is happen like on a sheet of paper, on a plane, right? Plane. So you have a few type of plane defect: external grain boundaries, twins, low angle boundaries, high angle boundaries, and so on. There are lots of type of planar defect here. 1, 2, 3, 4, 5, 6. So 7. There are 7 type of that one. So external surface plane defects. How plane defects can happen? So you imagine the external surfaces. So it's like when you break the surface, right? There's atom that connected to another side of the another side of the component. So you will form external surface. As you read, grain boundaries. We show you already what is grain boundaries when you do solidification previous class. So as you nucleus grow, then there's a space between the crystal. Then it become grain boundaries. This one you read lah. So this is the illustration of how the grain boundaries works. Right. So this is how you see on the SEM image. All these edge here, they are grain boundaries. As you read, as you read. What about twins? This one you will see in your experiment, lab experiment. So twin is a mirror image of structure axis cross the plane of boundaries. So as you can see here, you will see something like this. You will see there's like a runway. All right, a runway from the top. All these are twins. They are twins. Twins is like a same surface go parallel like that. Okay, all these are twins. So you should be able to identify. This one is on brass. You can see all these straight line, or I can say strips. It's called twins. All this you read, and yeah, all this you read on the screen. And twins boundary, they are good. They are good for material. This one, when we talk about how you strengthen material, in some case you are purposely creating twins in the material. You purposely make it up by process, by heating, and so on. Okay. So this is on the drawing. What I mean by twin that you see on the screen here, the plane actually overlapping each other, but in the straight line. Okay, this is called twin. But this one happened in a plane. Means 2 sheets of paper, same phase, same direction. Okay. Low angle, high angle twists, they are due to their angle. So this one you observe from the diagram given on the screen here. Then I won't ask you this one. Okay. So, but if you read textbook, you should know that when you see all this symbol, what does it mean lah? Okay, you see a T means there's a like an H, but this one in a plain form. Okay. So you observe on the microscope for material. If there's a space, open up like a crocodile mouth. You measure the angle on the boundaries, the top and bottom. There's an angle there. So if the angle more than 20 degrees, then it fall under grain boundaries already. This is how the material science they identify or they categorize the type of defect. If they measure the angle more than 20 degrees, it's under grain boundaries categories. Okay. Okay, the rest you read. Twist boundary means like one you see on the screen here, there's a twisting motion between the boundary. This one you can say as in the three-dimensional. It's the twisting of plane, twisting of plane. The last one, stacking fault. What I mean by stacking? Previously, I showed you the stacking A atom, B atom, A atom, B atom. When there's a stacking fault, means there's a mixture, there's an inconsistency between A and B stacking. Maybe we stack half already, then B go inside B and so on. Okay, so this is on the plane dimension. So the point here you can read. Okay. This is on an illustration on plane defect. So the bottom one, this is the darker color blue, is plane B, and the back one is plane A. So you can see there are some space. There's some space that can form between the space here, between the space between the two plane there. Right? Okay, the rest you read. The rest you read. It means that there's a possible of empty space that you can fit in alien atom there. Rest you read. So this is the stacking fault. Stacking fault means there is do not follow the sequence. For example, ABC, then AB suddenly become A. Then continue with A, then change to C. Right? So when there's no stacking fault means it follows sequence ABC, ABC, ABC. But there's when there's a change of plane, then it becomes stacking fault. Then we go upgrade a little bit in other three-dimensional, it become volume already. Plane is 2D, then it become, you upgrade a bit, become volume. Volume defect is easily defect by naked eye or under microscope, low power microscope. So it's a three-dimensional defect. Keyword for volume is three-dimensional defect. So it's a very big space is missing. And again, if it's a point defect, we use vacancy. If it's a three-dimensional defect, we use void or pole. Be careful on the wording you use. So if you see vacancy is a point defect. Then when you 2D or line defect, normally it's either 2 screw or edge. Then plane, you have a few like I showed you just now. This is a chart of type of defect. On the left table here is a type of defect. So you have dislocation, you have grain. And the dimension that you expected to fall into that category. For example, dislocation, the wave will be 10 power -8, about that. Grain will be bigger, the size will be bigger, and so on. Okay. So how does this diagram help you? Is that when you try to measure the defect on the microscope, then you get a certain reading, the space, the gap between atom and atom. Then you go to this chart, you try to observe where does the dimension fall into. Then you predict the type of the defect. Same with this one. So this is the chart used. On the left here is the type of the instrument you use. from scanning probe to optical microscope to naked eye. So this is the range that you can see, the size of the defect that you can observe, right? And this is, we are going into the way of detecting the defect. This is more on the lab component already. You'll see this one in a lab component. We won't test you in test or final exam. This is your lab report. So the rest you read. This is under lab report. How we prepare the sample. The keyword here is to make sure you have a smooth surface. This is all the steps to achieve that objective. You do grinding, you do polishing, you do etching. Means you expose to chemical to take out the chemical, the atom or element that you don't want. Then you observe under microscope. Okay, important is the clean surface. Okay, so you go through these steps when you come to lab. So this is the microscope that you will be using. Okay. And etching can be using UV light and so on. So this is incidence means incoming. You shoot the light and then it bounce back. So you have more energy means you can cut or remove more material from the surface. Okay. So the rest you observe from the slides. This one you will see when you come to your lab report later. Okay. This slide is important for your lab report. Okay. Yeah, so this is just information to feed into your lab report. Okay, then the next one is observation under microscope. Because of the type of the surface that you have, some got etching, some don't have etching. You will see different color under microscope. There's a dark color, there's a white color, because of the surface that you have. Okay, you'll see something like that. Some got edge, some don't have edge. Some got polish, some don't have. So you see the structure there. Okay. So this also part of the surface that you will be observing. This is the iron chromium alloy. You see the small dot here is the alloying element. Okay. So when you see all this black line in your experiment, it means that there is a reflection on the grain boundary here. Okay, you observe, and then the light will travel more to bounce back. You will see blue, not blue. You will see dark color line. These tell you the grain boundaries. Okay. So lab report, you need to explain the principle behind what you're doing. So this is what you see lah. Okay. There is a calculation to calculate grain size by a standard. So in engineering, in most of the time when you talk about experiment, there's a way of doing things. So we'll follow certain standard. For material engineering, we follow ASTM method. ASTM is American Society for Testing and Material. There's a certain code for that. So to calculate the grain size, we use this formula. Number of grain per square inch polish or etch. And the N is the grain size number. N equal to N minus 1. So this is the chart referring to STM. So grain size number 1 to 10, and nominal number of grain, you refer to the power that you use. On the middle column is one times the power. The one on the right here is 100 times the power. Okay. So what type? We have 4 general type: coarse, fine, and ultra fine. If your N number is less than 3, is a coarse. If your N is more than 10, is fall under ultra fine. Okay. So there's an equation to calculate average grain diameter, D, C, and L, M. So this is the grain diameter. Again, you have one more constant. C is a constant. Normally, you will use 1.5 for microscopic structure. M is the magnification that you use under your microscope. NL is the ratio of number grain to the actual length of the line determined. So we look at one example, how we use this formula for your lab report. So you are given a grain size determination, magnification 100. What is the STM grain size number matter if there are 64 grain per square inch? You use this formula, n equal to 2 power n minus 1. You substitute the number. So on the left, capital N was given. You have 64 grain per square inch. This is in square inch, right? 64 grain. Then you find the N, right? This is the exponential equation. Right? You use log. You log left hand side, log right hand side. You move the exponential to the front. Then you log the two. Right? You'll find the answer for N is 7. Okay. So this is how you find the number of N. So if you get 7, you refer to this diagram. You get 7. Then you identify what is the type of the grain you have. 7 is under fine grain. Fine grain. Then another example, example 6. If there are 6 grain square inch under microscope, you use 200 power. What is the SM grain size of the metal? Same. Right? So if there are 600 grain square at 200, so you just scale down from 200 power, you scale down to 100. You use 200 divided by 100. Then you square it. It's a factor you use to factor down. Then 60 gram per inch, like what you did for in example 4 just now. So you are dealing with exponential number. You use log left hand side, log right hand side. You get the answer. So this is how you find your N. N again referring to the table just now is still fall under fine grain category. Okay. One instrument we use in material science experiment is called SEM, scanning electrode microscope. The rest you read. The rest you read. So it's something look like this, very expensive. Minimum will cost you 1.2 million and above for one instrument like that. And you need a strong foundation that can absorb vibration. When you conduct experiment, because all these are used X-ray, very sensitive ray, your foundation must fit with anti-vibration mechanism. So like previously we went to UPNM, they have one. So when the technician conduct or the class conduct experiment, the PhD holder or master student, they conduct the using SEM, they will block the road because the lab is beside, like our lab here got the parking space there. They will block the whole parking space. There's no car that can go through the using the road lah, because the car will create vibration. So these are the example. This is a complete set of SEM machine. So when you go to a technical visit, when you see this machine, at least you know lah, oh, this is called a microscope and this is called SEM. Although you don't know the principle, but at least you look at it, you know what is this lah. At least you're able to say, oh, this is a SEM machine. Okay. The rest you read. Another type is called same principle as SEM, but this is called TEM, transmission electron. But the resolution a bit lower compared to SEM. This is a sample of image that you can see from the TEM. Most of the research university, they have this one. Something like that. You read lah. Read. So this is a type of dislocation and so on. This is a gallium nitride, H screw and mix. More advanced one is called HRTM. The one that I showed you just now is TM, but they upgrade the power of magnification. They call it high resolution, HRTM. Same shape like a pillar, like just now, but they add in more powerful sensor there. So it can look until very high resolution atom like what you see on the screen here. Right? And the rest you read. This is more in the NASA lab in the US. This one is in the atomic force microscope already. If you study for quantum physics, you want to get Nobel Prize, use this machine, right? You can look into very small tip there. This one normally you use this one when you develop new microchip. As you read. Okay. All these are very expensive equipment. Okay, with this we conclude chapter 4. The back of the slide here is there's a video you can watch when you have time, right? This is how they do it. I'm not sure whether you can play or not. Okay, you click this link and then you watch in the lecturer slides later. So at the back of the slide, I'll give you some sample of question. Right, you can try to solve. Okay, this we conclude chapter 4.